here. So the length is like L3, okay, and you have got the plate inclined at an angle theta. Okay. So these plates are inclined at angles theta with the horizontal, and then there is a how this look like. So now, if you try to find out, T is LP by VH theta, and so LP and your VH theta is the velocity in this direction, okay, and you have D. D is the distance between the plates; it moves in this direction, and D divided by VT cos theta. Okay. So this is how it will look like, and so you get VT equals to VH theta divided by D, and you have LP cos theta. Okay. So and also your VH theta is nothing but again Q by N into D into W. Okay. So this is how we can define our velocities, and so these are the three types of the system, and the angle of here, the angle is best if you can provide like 90 degree, but it is not so prudent to keep 90 degree, and it has been seen that the efficiency is much better when your angle of inclination with the horizontal is kept like, theta is greater than equals to 60 degree. Normally theta is given as 60 degree. So general tendency for the manufacturers are like giving theta equals to 60 degree or 70 degree. So this is what we actually have, and most of the times people tend to provide counter flow systems. So this is much more preferred, although here there is a better solids removal because of the co-current system, but the constructionally and maintenance wise this is not so easy to maintain, because sometimes what happens is that in this portion, if there is a deposition, then obviously you cannot really maintain this. So operationally simple is this, and this counter current system is preferred. Now, so these are all plate settlers, and in the next generation was like tube settlers. But let me first have give you a glimpse of the photographs of how they look like. So these are some photographs of how they look like, and you can see these are the plates, and you can understand that your water is moving like this from here, here and here, and the particles tend to settle like this. And so if you look at the projected area, if this is having an area of A, each plate, and now your projected area is only this small area A, which is your projected area. So you can see, you can actually have, while you are inclining this, you are actually having, huge amount of settling area incorporated in a small footprint. Okay, so this is the better system, and so you can incorporate if there are n number of such channels, then you can actually incorporate total area of total area is n times A, and you can understand that so much big amount of area can be incorporated here. Okay. Now, how they actually are kept here? You can see here that if you look at this diagram, you'll see that these are all the plates lined up. So if you see, these are the plates. You can see there's a stack of the plates right here. So each of the plates are stacked like this, one after another, parallel to each other. And these are stacked like this. And on the top, if you are able to see, they are aligned here. So now the water, what happens is that the water enters from somewhere here and it comes out from like this. Okay, it comes out through the stuff like this, but the channels are actually, you can see the plates right here, but I have drawn these plates, but they are not actually exposed at the sides. So the side is closed. If you see, this side is closed. Okay, so the water doesn't have any other ways to go, but it has to come out through the plates. So it comes out through the plates, and when it is collected over the plates, and then you have an overflow channel from where it will be collected. So similar to the treatment plants. So here is another view. You can see here that water goes in like this, and it comes out from here. And if you can see, these are the plates provided here like this, and they come out from the plates, and then there's overflow channel, and they get overflow on the overflow channels, and then it will be carried out from here, depending on the slope. So everything comes up, and the clear water is collected in a trough. So somewhere here there will be a trough, trough provided where the overflow will be collected. Okay, so the troughs will collect the overflow, and this will go out like this. Okay, and this is another photograph showing the assembly being lowered into the system. You can see, at the sides they are closed. All the sides they are closed. Only from the bottom the water can enter. Okay, let us have another photograph here. Let me show this photograph. This is again a bank of pure plates. You can see from the top. These are the plates that you can see from the top. Okay, and you can now see that the water comes up from here, and then it goes into this trough. You can see this trough where the treated water is collected. So there is no way that water can come up from any other space. So it goes into the system from the bottom, it enters, and from the top it overflows and comes and puts in the trough. And these troughs are connected somewhere. You can see at the end, probably at the other end, they are connected. And now, these plates are made of mostly made of FRP. So this is fiber reinforced plastic, which are very light and very easy to handle. So normally they have. So this is the top view. Let me write. This is the top view here, and they can be actually, maintained very easily from the top. If I have this photograph, no, I don't have. But anyway, so a person can stand over the plates and can have a high pressure jet, and he can clean all those plates which might have been clogged. Or these plates are so, light that because they are FRP made. Normally the width of the plates are like, this is like 1 to 1.2 meters. So between 1 meter to 1.2 meter with also plates, and so a person can very easily hold and take this plate out, and with a jet of water can clean the plates and put it back there. So the maintenance is very easy for this type of plates, and you can pack number of sedimentation basins within a very small footprint of area. So this is why they are getting very nowadays all the new treatment plants, they have this type of plate settler or tube settler in position, rather than having gigantic sedimentation tanks. And in many cases, the existing sedimentation tanks are being retrofitted, or being modified to accommodate the plates so that their efficiency is increased. So see here, if we have, this is the diagram here, where this is, you don't look at these plate settlers here. So this was earlier just a sedimentation basin. You can see there was like overflow position and all. Now what we have done is that we have added the plates over here. Just put the plates, made a small structure and put the plates here. And when you have done so, your sedimentation area actually increased, and this is how you can see that they have been, you can see these particles, this inside this, they are, getting removed, the solids are getting removed. So this is how the existing treatment plants can be also modified. So this is a combined system, okay, where it's kind of a retrofitted system, okay. Now, and here you can see the flocculator paddles and everything right here. All right. Now, in many times we do not provide the plates, but in place of plates, we provide small tubes. So if you look at the tubes, then it's like probably you have seen the some of the crates in which where the cold drinks are kept, bottles, the glass bottles of cold drinks are kept. So this type of crates or individual units are there where you have put a lot of plastic tubes are there where you can have square aperture. So this is one of such things. You have square apertures, okay, square apertures, and these square apertures, each one of them is like is your one of the channels. So if you look at the plates, plates were like this. But if you can think that in place of plates, we have small tubes, placed like this. Okay, so they play the same role here, and so this is the tubes, and the whole thing will be placed inside your settling basin in an inverted position, so that you can have the similar function here. So, and you can have circular cross section. So all these are put like an inverted position inside your tank. Okay, so you can have rectangular tubes. The tubes can be hexagonal. It can be layers in alternating directions, and it can be chevron type. So you can see this it's a chevron type of cross section. So this probably has a better section than anything else. So this is like a chevron shape stuff. Okay. So there are different types of configurations, and all of them are called tube settlers because they are not plate settlers. They are relying on tubes. Okay. So next, I will come to some mathematical examples, but before that, I want to, very quickly go over other types of advanced treatment, settling devices. We have already discussed, or you have already learned about, normal settling devices. Now, this what we are talking about: high rate settling devices and high rate systems. So this is one system. This is called a reactor clarifier. So this is called reactor clarifier, mainly because here you can use them as a reactor, as a clarifier also. So you can see here, this is nothing but a kind of a clariflocculator, where flocculation, coagulation, flocculation, and settling, or the clarification, they take place in the same system. So what is this? You can see there will be chemical addition. There are these are, look at the structures. So there is a tube through which the water comes in, and then it gets exposed into a separate chamber. And in this chamber, what is there? You have a mixing condition. So you have a, let's say, flocculator, and this flocculator turns here, and when you have chemical addition, flocks are generated, and these flocks are actually now passes over to the other chamber where the settling actually takes place. So here you can see this water with flocks, they enter this chamber, and here it is more or less like a small sedimentation chamber, and where the sludge or solids will settle as sludge, and at the end of this chamber you have a wire through which the water, clarified water will come. So, and what happens is that here a blanket of the sludge is provided, so that the solids are always in contact with, it's in a dynamic condition, and this actually has shown to be better than normal clarification tanks. Now this one is it's called a solids contact. It's called a solids contact or sludge blanket type of reactor clarifier. Here, this is not only a clarifier, but it also acts like a filter. How? See, you have, you put the water through this. So you have a chemical added online, and the water comes here, and it comes out like this. Okay, and you maintain, here you actually create a vacuum. So this is connected with a vent valve to release vacuum. So this is connected with the vacuum pump. So what happens is that whenever you start running this vacuum pump, the water level here will rise under the vacuum, and then this pump you can start and stop. Then when you release the vacuum, it falls, okay, and and again it rises like this. So there is a pulsating type of behavior created here because of this operation by the vacuum pump. Now you can see here that the water, actually the untreated water or the flocculated water, comes out through pipes, through pipe holes, and it tries to go up like this, and when it tries to go up, at the end there is a plate settler. You can see plate settler. So the particles that will be collected by the plate settler, they will come and they will collect it like this. So here there is a dynamic situation that there are solids trying to settle down, solids trying to settle down, but water actually tries to move the solids up. So you have to, if you can create or control this situation very nicely, then there will be a blanket of sludge that will be formed. Okay. So there will be a sludge blanket will form, and this sludge blanket will be a thick layer which will be floating here, but will not be settled. And while the this water tries to come out, the sludge blanket with lot of solids, they will act like a upflow filter. So the particles in your flux, they will get adhered to here and filtered out, so that clean water gets passes through this. So here the clean water rises, and then it goes over through this and gets collected into these wells, from where they are taken into into their application plan. So then you can see that here not only settling, but kind of an entrapment in the form of filtration that takes place here. So this is called solids contact or sludge blanket clarifier. And then we have another type of it is called this is known as so this is known as ballasted clarification system. Okay, so if you can see here, we have same tank here, and we have influent coming in, and there is a addition of micro sand and polymer. Why this is like this, and then there will be coagulation, and maturation means flocculation. So this is flocculation, where the sludges will be matured or made bigger, and then there is a sedimentation tank, and this is your plate settler provided. Okay, so everywhere you see a plate settler, only to reduce the area requirement. Okay, so how it works, you see this influent is coming. Now polymer addition, we understand why polymer should be added, because this is like the coagulant. But many times what happens is that you provide coagulant, but you don't see any flux, because you have to have the way flux are produced. Normally you have to, there should be a nucleus, or a very small particle, along which this flux will form. Okay, and they will bind to this nucleus, and this is how the flux are formed. Okay, and many times the occurrence of the nucleus is like a chance phenomenon. But if you provide nucleus from the outside, the process is very fast. Okay, so this micro sand is added as the nucleus. Okay, and sometimes it is called a coagulant aid. Okay, so coagulant aid. So micro sand is added from the outside as a coagulant aid, across which the whole flock formation takes place. So now if you see that micro sand is getting here, and you have the sedimentation, and you have a very efficient removal here, so that because you have provided the nucleus, and over which the flocks will start forming, and you have bigger size flocks. But these microsands are also not so easily found. They are expensive or they are bought out items. So what happens is that the sludge is settled, and then we take the sludge to to a hydrocyclone. Why hydrocyclone? In hydrocyclone, this is nothing but a centrifugal device. So where because of the centrifugal action, the sand is separated out of the flock after the sludge is collected. Okay, so and so that when the separated sand is separated out, this sand is again collected and then reused. Okay, so reuse is something which is very important here, because these microsands are not expensive, so you need to reuse these microsands. Okay. All right. Now these are some of those phenomena that we have talked about the settling basins. There are so many things that we need to talk about settling basins. About the efficiency of settling basins and all. I'm not getting into the details of it. So you can actually, try doing, going through some literatures or maybe books to find out more, because this is not exactly what we want to deliver in this course. But again, when we affecting performance of sedimentation basins, there are a few factors which are very important that we need to know. One of those, are inlet and outlet structures. Okay, so if you, as I have told you, that when there is a sedimentation basin, the sedimentation basins. Okay, and in the inlet we also have some structure called baffles. So we can have some structure called baffles. These are nothing but energy dissipation devices, because when you feed this tank, the water comes in a pipeline. Okay, and pipeline, you can understand the velocity is quite high, so it has got a kinetic energy. But inside the settling basin, what you need to have, is like, so inside the settling basin, what you need to have is a very quiescent condition. So you have to maintain a very quiescent condition so that there is no turbulence. Okay, and so that the particle, it actually can settle down at the bottom without getting disturbed. But if you do not have a very good outlet structure provided, then the particles can scour out, and again some of them can find their way into the outlet. So one good design would be just to prevent the scouring, and also the energy dissipation should be there, so that the energy in the water is very less when it is in the tank. So that we can we should have the turbulence to be avoided. So no turbulence. Okay, and horizontal velocity should be so that no back mixing is taking place. Okay, there should be no back mixing. Okay, and how to say that our turbulence and everything to be avoided. Now, if you can say, see that turbulence is given by Reynolds number, and there is another number called Froude's number. These two are very important to check. Okay, so in case of Reynolds number, we can say this is rho velocity of horizontal velocity, and this is RH is the radius of the tank. Okay, I would say hydraulic mean radius of the tank. Okay, and divided by mu is the viscosity of water, and Froude's number is given by VH square by GRH, where RH is the hydraulic mean radius, and so RE should be kept less than 20,000 for and Froude's number should be greater than 10 to the minus 5. So these are the two conditions that we want to see for horizontal flow rectangular basin. All right, and so there are other effects. We have density currents. Okay, density currents because of difference in the density, because at the top density will be low, at the bottom density will be high. There will be density currents created, and then temperature differentials at the top, because it will be, if it is open to the sunlight, then the top part is warm, below is cold, so there will be convection current created. And then we have wind effects. Wind blowing, strong wind blowing will cause some more velocity in the tank. And then of course we discussed inlet and outlet structures. They actually they are very important to prevent it. All right, so we will talk about this later on, or maybe if you are interested you can get into some books, but right now try to find out some try to do some numerical work. Okay, first one, let me start from a very very rudimentary design. So design horizontal flow settling tank. Okay, with following details. Okay, so Q equals to, let's say, 3 meter cube per second, and we have density equals to 1000 kg per meter cube. Okay, and settling velocity for alum flow is 2.2 meter per hour, and mu is equal to 1.3 into 10 to the minus 3 kg meter per second. Okay, and provide at least two components. Provide at least two components for the use. Okay. All right. So fine. So Q is let's say 3 meter cube per second, convert it into meter cube per hour. So you have 3 into 3600, all right, second hour, and then you have meter cube per second. So that gives us 10800 meter cube per hour, right? And they have said 2 compartment. Let us, think about. Let us provide 3 compartments. Okay. Okay. So, or 3 number of vessels. So what is and you have settling velocity for Adam's law is this. So you have V0, which is equal to 2.2 meter per hour. Okay, and this is nothing but equals to 2.2 meter cube per square hour, right? And so we know V0 equals to Q by AS. Okay, what is the Q? Because we are dealing with each compartment, then how much flow is there? Q by 3, right? Which is our new Q. Let us write Q1 is equal to 1800 divided by 3, which is 3600 meter cube per hour. So each of this having 3600, so we can write. All right, let's just do it this way. Let us not do this right away. Let me try to do it in another way. Okay, so you have 1800. Okay, all the flow is that we are using. So this is and divided by AS. Okay, and you have V0 equals to 2. All right. So that gives me AS or total surface area equals to 10800 divided by 2, which is equal to 4909 meter square, right? So this is 2. I have done this calculation before, so I can write. Otherwise you can also calculate. So we will use 3 compartments. Okay, so each compartment the surface area is how much? Surface area is 4909 divided by 3. Okay, and let's say this is almost equal to 1640 meter square. Okay, now normally the length is to width has to be greater than 4:1. So this is a normal scenario. Let us take L is to W equals to 5:1, and so you have 5. L times W equals to 1640, and now you have L equals to 5W, so 5W into W equals to 1640. So from here it is done. Or you have W square equals to 1640 divided by 5, and I have calculated this is 18 meter, close to 18 meter. So let us provide L equals to 18 times 5 or 90 meter. So from here, if we calculate 1640 divided by 18, let us provide 92 meter. Okay, so let us provide 92 meter by 18 meter each of these basins, and there will be 3 vessels. So you have 19 meter, 92 meter is the length, and then you have 18 meter width and 18 meter width. So this is like 18 meter, 18 and 18. All right, fine. So this will be your surface area. Normally detention time is given as so normally the detention time is provided as about 1.5 hour to 4 hours detention time. So if we say the depth is, just trying to think that depth is 4 meter, which is, if you provide higher depth, this is very highly cost prohibitive. Lower depth means there are the chances of scouring. So good depth will be 4 meter. So if we provide 4 meter depth, let me find out the value of detention time. So we have 92 meter divided by multiplied by 18 meters, this is the surface area, and 4 meter is the depth. And if you divide it by total flow rate, 10800 meter cube per hour, and we have 3 such vessels, right? So this will be the so you can see T equals to E by Q, right? So this is the volume, total volume, and this is Q. And so we get it, I did some calculation and we got 1.84 hour. And this is between 1.5 and 4. So this is okay, all right. So your basic dimensions are like 92 meter by 18 meter by 4 meter depth. Okay. Now let us calculate the horizontal velocity. pH is how much? So if you see, this is your 3 tanks, 3 tanks here, and these are this is how it would look like. And so your cross section for each tank, what is the cross section velocity? You have 10800 by 3. So this is, if you see this, each of this tank is W here, and H is the height. So your pH is nothing but equals to Q by H into W, right? Okay, so you have 108,003 for each of these vessels. Let us write Q1, and you have 18 meter and by 4 meter, right? And which will give you 0.83 meter per minute. Okay, and our system, if you look at any book, we see that pH should be between 0.3 meter and 1.1 meter per minute. Okay, so this is also passes this test. Okay, now if you want to check for Reynolds number, what you get is, if you look at the formula that I have written for the Reynolds number, rho pH by RH by V. So this is equals to rho pH RH over V. Okay, so we know the value of pH, but we do not know RH. So RH is what? The hydraulic ring radius, which is given by the area of flow divided by weighted perimeter, right? So if you look at this, what is area of flow is 4 meter by 18 meter. Now because width is 18, and you have, so this is 4 by 18. So this is your cross sectional area divided by P. So top is not like weighting any surface, but the sides are weighting the surfaces. So what you get is you see 4 into 2 plus 18. So 18 is the bottom, and you have two sides of 4 meter each. So this is your perimeter, and so this comes to equal to 2.77 meter. Now if you plug in the number RE, so you can see rho equals to 1000 kg per meter cube. Okay, 1000 kg per meter cube, and you have VH, which is 0.83 meter per minute. Okay, times 2.77 meter. Now V cannot be in minute, so I put divided by 60 to convert it into second. Is that to provide some more compartments, your RH is now lower. You can see that if you can actually have lower number of R. Okay. Now in this case, provide take each of these channels and provide 3 longitudinal baffles. Like provide 2 longitudinal baffles like this. So each of these compartments will like 18 meter के अंदर inside this 18 meter provide longitudinal baffles. Okay, so that you now have 3 compartments. Okay, 3 more compartments in each of them. Okay, now with this, now you can see what is the value of RAs that you are getting. Again, write A by B. A is, each of them is 6 meter. Each of the width is now 6 meter, and then you have 4 meter depth, from the very beginning. So the depth is like 4 meter. So 6 meter by 4 meter divided by, P is now what? So this you have 2 into 4 as the same. Only then you have put like 3 compartments. So you have 2 into 4 just like this. And now in place of 18, you have what? 6. Okay. So you get a number here 1.7. Alright. Now plugging this value here, R equals to again 1000 kg per meter cube and 0.83 by 60. Okay. Square into 1.7 divided by 1.3 into 10⁻³, and this gives you 18261, which is less than 20,000, and we can say this is okay. And then you can say Gauss number. Try to find out Gauss number GRH. and as I have calculated, this is 1.17 to 10 to the minus 5, which is greater than 10 to the minus 5, and this is okay. Alright, so this is how you can calculate this basis. Now if we try to, I'll take another 5 or 10 minutes, just be patient, stay with me. So now if we have, again, if we want to design if we want to design this as a tube cylinder or plate cylinder, how this design will help us getting low footprint area. What is the footprint area that we have here? You can see we have 18 by 18 by 18 by 19. So this is the area that we need for our treatment, for our septic tank to install, to get installed. Now, if we provide a tube sector, then what is the area that we are talking about? Okay, so now try to see that we have 3 compartments. Again, think about, we have 3 compartments. That is that is what said that provide at least 2 compartments will provide the same as like 3 compartments. Okay, and each compartment will have a flow of how much? Each compartment is going to have a flow of 1 meter cube per second, because the total flow is 3 meter cube per second. Okay, so each compartment is 1 meter cube per second, and this is like 3600 meter cube per hour. All right, now let us use tube cylinder modules, of 50 millimeter square cubes, 50 mm square cubes. Okay, and so this, you can say that, and let us consider that vertical height of the tubes is 0.6 meter. Why I am taking this value? Because this is the standard size that is available in the market. So you can now say, and also consider that angle with the horizontal, So these are standard things that are available is 60 degree. Okay, so then your tubes would look like this, your module would look like this. So module has number of tubes, so it has got number of tubes inside. Okay, and each of them are like inclined at 60 degree with horizontal. So you have tube modules. So you have these tube modules which are inclined at 60 degree with horizontal. Okay, and so your water will pass through each of these tubes and will get collected from the ground. So this is how it is. Now if I draw each of these tubes, try to draw each of these tubes here, and again, this is your pH theta. Remember what we have done, and here we are saying that the angle is 60 degree. Okay, and you have the height of 0.6 meter. Okay, they are not saying the LP. Okay, so LP is that what we have decided, that LP is the slant distance. Okay, so this is how we found out our values, right? And the tube modules are 50 millimeter square inch. So that means this tubes are, if they are square tubes 50 mm, so the gap between each plate is 50 mm, right? And there will be settling velocity is Vs, and we know Vs equals to, for Allen flow, this is given as 2.2 meter per hour. So that's, you can see here, this is 2.2 meter per hour. So these are the data that we are having, and let us try to find out, what are the, so let us, so here H equals to LP sine theta, right? If you look at this diagram, H equals to LP sine theta. So then we can write LP equals to H by sine theta, alright? Because we know H, not LP, so we have, but our formula has LP here. So let us find out the formula of Vs equals to, see here, we have derived this formula here, is that T or Vs equals to Vs theta d by sine theta LP cos theta. Okay, so let us try to write this formula here. Okay, so Vs or Vt, whatever you say, is Vh theta into T divided by T sine theta plus LP cos theta. All right, and let me write here. This is if you see this, Vh theta is nothing but Q over A sine theta, where A is your footprint area, right? So you can say that Q by A sine theta in place of Vh theta, and you have T by LP cos theta plus T sine theta, right? Now in place of, so you can write this is Q by A, and you can write LP sine theta. So you just multiply here LP sine theta cos theta plus T sine squared theta. Just multiply with sine theta here, and so you get here Q by A into T by LP sine theta means LP sine theta means H. Okay, so I will write H cos theta in place of LP sine theta, write H plus you have T sine squared theta. All right, and now plugging the values, you have Q by A, okay, and you have T equals to 0.05, like 50 mm equals to 0.05 meter. All right, and you have H equals to 0.6 cos 60, right, plus T equals to 0.05, and you have sine square 60. All right, and this should be, and this Vs equals to nothing but 2.2, okay, 2.2 meter per hour. Now you know the value of Q, okay, which is 1 meter cube per second, or 3600 meter cube per hour. Everything else is known but A. So you can now calculate A, and if you can calculate, you must to know A is equal to only 242 meter square. And in this case, you can see here the A value was how much? The A value for each of them was 18 meter by 92 meter. So which is which was like 1640, and here we have only 242 square meter of area that is required. So you can see here only, if you can use this, you can reduce the footprint area by a big margin. Okay? So let me stop here. It's already more than 1 hour, and we will conclude this particular example in the next class, and then we'll go over the next topic. All right. So I will upload this slide today, and please go through this and try to find out if you have any question. And probably this particular example for fluid cycler is not yet done. We will complete this problem in the next class. But as far as we have done, you can understand that our area requirement is very, very small in this case. Okay. All right. So sorry for holding you for a longer duration of time, and if you have any question, you can ask me now, or maybe in the next class you can ask me. And for the time being, let us. Yes.
Sir, can you move to the slide where you explained co-current system?
Where I have explained
co-current system, sir.
Co-current system. Okay. So let me show you the co-current system. Yes.
Yes, sir. Here, in place of VX, there should be D, I think.
In place of
where?
Probably Friday. I'm not sure whether Friday we don't have any class because of it's a national holiday for observing Muharram. But probably this Saturday class will be a Friday. Although it shows in the routine it is Thursday, but it should be Friday. Let me hear back from the academic section. If not, it is a Friday, then we are meeting again on Monday. Okay. All right. But I will let you know because I will send you an invite if there is a class on Saturday. All right. Thanks for being with me, and I'll see you in the next class. Bye.
Thank you very much.